So let's get into some details. So one of the ways we can determine, how do I know if my part is good or bad? Where do I set that value at? Where do I set my thresholds? A lot of times when the part is engineered and designed, it's been designed to do something specific, and so a specification could be handed down saying this part needs to be IP rated, for example. Ingress protection is where we're trying to make sure something is watertight to a certain depth, watertight to 1 meter, watertight to 10 meters. So knowing that spec, we can transfer that in and say, okay, where does it stand as far as an air leak? What does that mean? So we make a device that we call a leak standard. It is that spec in physical form. In essence, it's a calibrated leak. Now this calibrated leak is the line to which your specification would be. So something that needs to be watertight, based on our other customers and our history and our experience, we understand that for something to be watertight, air can actually leak out of it. And there's a certain amount of air that can leak that will tell us if it's less than that amount of air, then we know that water won't leak out. If it's greater than that air leak, water will leak out. So for example, 2 cc's per minute seems to be a spot where we can get air to leak out of the system, but when we apply the same amount of water, water won't come out of the system. So we can make that into a calibrated leak with a traceable calibration on it. So when I run this test again, what I can do is, if this is my golden part, my master part, what I can do is run the test, find the result, and then I can add in the known leak rate that would cause a failure. Now when we're just starting out, this will let us understand where do we stand. If I was to put a part on there that had the actual leak, could I discern between my master part and a part with the leak? And what you can see, there's a faint line here that shows the previous test, and then this dark line, the brighter line anyway, shows this test. And the separation between the two, there is some separation, but there's not a lot. So we have a rule of thumb that we like to use, is that the separation between a good part and a bad part should be 3 times each other. In this case, we had 0.033 for a good test, and when we added the leak standard to it, now we get a 0.042. So that's not even, that wouldn't follow our rule of thumb. It doesn't have 3 times the separation. If I have a 0.03 on a good part, I want a failing part to be 0.09. Now that we've shown that we can test the master part by itself and we get the decay, and we test the part again with a known leak rate value on it, we can see the difference between those two values. And we can see that there's not quite enough separation to draw a line in between and declare one part good and one part bad. We're not following the 3x separation kind of a rule. What do? So what we can do is we can start to manipulate times in the test to allow us to get those values to grow. Those 2 timers are going to be the fill timer and the test step timer. What they're going to be doing is, if we took our values on a number line and we graphed the values we got, we want to be able to get our parts to start getting more repeatable, closer to each other, that we're getting a very repeatable test. Because we're nullifying the thermodynamics and the elastomeric creep that we've talked about previously. So by changing the fill time, I now take the variance of what those parts could be on the number line, and I start to shrink it and bring it down. Once I get that sufficiently shrunk down, I can now adjust the test step time to start to separate the values. Because the idea is, a good part is going to not decay as much or stop decaying, where a part with an actual leak will continue to decay over time. So if we took the test step time and stretched it out, a good part's decay would level off and stop, where a leaking part would continue to decay more and more. So the further out we go, the further those two values separate. And when they get enough separation, we can stop there.